Okay, so today, well, we kind of left last lecture with this, I wouldn't call it a negative statement, but a statement of limitation, which is the fact that when you write down the necessary conditions for optimality, and we did this for a linear quadratic problem, you wind up with a situation where you have to solve this boundary value problem. And the boundary value problem can get difficult to solve if you're integrating over a long period of time. Which clearly can cause an issue when you have any real problem where the dynamics are nonlinear and you can't do things analytically. There's another aspect to this which I haven't discussed yet, but I'm going to just go over it briefly, and then we're going to go on and we're going to start talking a little bit about numerical methods, which is that this concept of path constraints. All right? Now, path constraints are exactly what the term says. They are constraints that limit what the state and or the control can or cannot be. They don't have to be direct limits on the state and control. Those are path constraints too. But they can be functions that are of the state and control. Now, what would be an example of this? Well, if you think of like a physical problem of, this is kind of maybe a stupid example, but it's something you deal with every day in your life. When you're driving on the road, right? If you want to go from the MAEA parking lot, to the mall, you can't go drive on the sidewalk, right? Well, you can, but you're probably going to get a ticket if you do that, right? So you're probably, worse than that, the pedestrians and stuff, you don't want to get into that, right? The point is that you stay on the road. Well, the road effectively has limits, right? It's got a limit on one side, you can't drive on the other side of the road because there's traffic coming the other way, right? So you got to stay on the right side of the road, and you got to drive in certain directions. You got traffic lights. Those are path constraints, right? They constrain not only they're not constraints on necessarily physically what you can do. They're constraints geometrically as to what you can do, right? You can't just drive anywhere you want. There are also physical constraints, right? You cannot, your car, now remember, we're doing all this with modeling, right? So your car, you can say that, well, I want to be able to just accelerate as fast as I can, or as fast as I want. Well, clearly your car doesn't have the capability of accelerating just as fast as you want it to, right? It's got an engine. The engine has a limited amount of power. So you can model anything you want, and you could say, well, I have unlimited amount of power, unlimited amount of torque, and I can accelerate as fast as I want. But the reality is, even if you did model it that way, your car could never do that. So you would want to come up with a more realistic model as to what your car can do. So that's a physical path constraint, where you're incorporating what the vehicle or what the object is that is moving, what it can actually do as compared to what you could idealize it to do, right? So these constraints have this following form, where we say that we've got a function c, which is a function of the state, and it's a function of the control, and it's a function of time. Now, these are vectors. We can write this in one of two ways. We can either say that it's bounded by some minimum and some maximum, but for the purposes of the theory, we normally write it in an alternate way. Because if you look at this constraint, you can actually rewrite this constraint this way. This is not a this is kind of a dumb way to rewrite it, but it allows you to be able to make the form a little bit simpler. I can say C is less than or equal to C max, right? Because that's the first constraint. And I can also say that C is greater than or equal to C min. If I take the second of these, right, and this second constraint says that what? It says that minus C min is less than or equal, it says that, write it this way, C is less than or equal to C max, and minus C is less than or equal to minus C min. So we could construct a new vector. We could say let, we'll call it K, equal, I could say C and minus C, and then I can rewrite this whole thing, or let's rewrite it this way, C, and then I could subtract plus C min, and then I could say this is C minus C max, and I could write it as K is less than or equal to 0, right, if I write it that way. Now, that's just another way of being able to write. So we're just going to write it without getting into all these mins and maxes. We're just going to always write C of x of t and u of t and t is less than or equal to 0, just because it's a little easier to do it this way than it is to have to keep worrying about mins and maxes. In a real problem, you will have to worry about the mins and maxes, but for the theory, it's just as well that we write it this way. Now, if you look at this problem, let's go back to the calculus of variations. So back to the variational form. So we've added an inequality path constraint to the original problem. Which means that because this is another path constraint in the problem, clearly there's got to be a Lagrange multiplier associated with that constraint. Just like there was a Lagrange multiplier associated with the dynamic constraints and the boundary conditions, there's got to be one associated with the path constraints. So the augmented cost functional in this modified problem, now I'm not going to rewrite the entire statement from the beginning. I'm just going to write the augmented cost function. So the augmented cost functional is still going to have the Mayer cost. It's still going to have the Lagrange multiplier on the boundary conditions. But now what I'm going to have is I'm going to have L, and I'm going to have plus lambda transpose F minus x dot. And now I have a new multiplier, minus mu transpose times C, which has to get added into it. This new one, this is due to the path constraint. Now, the problem with this path constraint is, unlike the dynamic constraint is an equality constraint, right? F minus x dot has to equal 0 along the entire trajectory. So as a result, that path constraint is active everywhere. It has to be active everywhere, right? But this constraint here doesn't necessarily have to be active everywhere, right? I could have a situation where C at certain points on the optimal trajectory is less than 0, right? If C is less than 0, it's as if the path constraint wasn't there in that part of the solution, right? Because it's not binding. The only time this becomes a problem is when this path constraint becomes binding, which means that you could have a situation just qualitatively, we could write it this way. Let's suppose that this is C as a function of t. And we've got some limit. I put some limit up here. And I've got some lower limit. This is very qualitative. And the value of C on the optimal trajectory looks something like this. It hits its lower bound. It follows its lower bound. It comes up. It hits its upper bound, follows its upper bound, and then say it comes off, right? So in this region right here, the path constraint is active. And in this region right here, the path constraint is also active. Now, this is a bad drawing because I said that C was less than or equal to 0. So maybe I should redraw it like this. Let me redraw it just to make it consistent. Rather than I was thinking of doing it between C min and C max. So let's do it more consistently. So let's say this is. I'll do it like this. Let's say this is 0, right? And I'm forcing C to always be less than or equal to 0. So C is less than or equal to 0. But there's a segment where it actually becomes active, then it becomes less than or equal to 0, and then it becomes active again, and then it comes off, right? So this is t, and this is the value 0, and this is c. So in this region right here, the constraint is active, and in this region right here, the constraint is inactive. Everywhere else, these two regions right here, it's active, and here it's active. Everywhere else, it's inactive. So wherever it's inactive on the optimal solution, if I remove the constraint from the problem in those regions, it wouldn't change anything, right? Because it's not active to begin with, so it doesn't matter that I enforce it. But in the regions where it's active, it does matter, because if I didn't enforce the constraint, the solution would want to actually violate the constraint, right? But I'm not letting it violate the constraint because I'm saying it has to stay less than or equal to 0. So the way we deal with this is when we write this modified problem down, you could see that everything in this problem is exactly the same except for one thing. I have L plus lambda transpose F, which is the original Hamiltonian, and then I have this other thing over here, minus mu transpose C. So we define what's called the augmented Hamiltonian. And the augmented Hamiltonian is the original Hamiltonian. We call it H sub A. It's the original Hamiltonian minus mu transpose C. So this is going to equal L plus lambda transpose F minus mu transpose C. Now the problem with the constraint is the constraint may or may not be active, right? So what happens is that this multiplier is mu. Mu takes on the following form. What happens if the constraint at any point in time, and when I say this, this is mu of t. So mu star of t if you really want to get technical about it. If the constraint's inactive, what does that multiplier have to be? 0, right? Because if it's not 0, I'm going to be adding something to this function which can't be there because the constraint's inactive. It's as if it wasn't there. So if mu star of t is equal to 0, it means that c has to be strictly less than 0. What happens if this constraint is actually active at a point, which means that c is actually equal to 0? Well, the multiplier may or may not be 0 at that point, right? Because it's going to be non-zero. It doesn't necessarily have to be non-zero. So what we do is we say, well, it's going to be less than or equal to 0 if c is equal to 0. This is just due to the fact that I chose that convention for the negatives, for the sign. Okay, it has nothing to do with anything else. All right. Now, you could see the problem with this. The problem with this is I have no idea how I'm supposed to figure out mu. I have no condition for mu, right? All it says is that this is what's called complementary slackness, by the way. This condition is what's called complementary slackness. What all complementary slackness says is that I have a multiplier that could take on a non-zero value, but I don't know if it's going to take on a non-zero value. Ahead of time, I don't know, right? Because I don't know where the constraint switches from being active to being inactive. So the problem with this is that when you deal with these kinds of constraints, when you now you're adding to the optimality conditions, because remember, all these other optimality conditions that I derive have to set the first variation in that augmented cost functional to 0, right? Now I've got these additional conditions on this multiplier mu that I have to deal with. The problem with that is because I have no algebraic or differential relationship to be able to figure out what mu is, I have a problem in terms of being able to determine the switching structure of the path constraint. So you've just complicated the problem an immense amount by adding this path constraint into it, because now you have to know something about when the constraint's going to become active and when it's going to be inactive in order to be able to get yourself a solution. So basically what you wind up doing is you wind up doing this kind of weird searching thing where you say, well, it looks to me like the constraint may be active in these regions. Let me try to make it active in those regions and then solve the problem as if it were an equality constraint in those regions, and then I'll see whether or not, see what the solution looks like. And then you keep doing that by trying different regions where the constraint may or may not be active and see what happens to the cost. Well, that's a very ineffective way to do this, right? Because you still are guessing. You're effectively guessing, right? So guessing isn't a good thing. You don't want to be guessing. So this leads into the fundamental problem, which is that the calculus of variations conditions that you're going to get when you have a path constraint are going to get so complicated that you no longer can just apply all the elegant things that we could have done before. If you're doing an indirect shooting method, for example, when you integrate, if at any point along the trajectory when you integrate by guessing that unknown costate, you violate that path constraint, that's not an admissible solution to the problem, right? So how are you going to enforce the path constraint when you have to integrate these differential equations, these state-costate differential equations from one end to the other, and you don't know when you're going to violate the path constraint until you actually get there, right? So every time you take a step in the integration, you have to check to see whether or not you violated the path constraint. And if you do, then you have to play all these hokey games about, oh, I violated the path constraint, so then I'll just assume the path constraint is active and then try to keep it on the path constraint for a certain region, but then you don't know whether the constraint ever goes inactive again, right? So what this comes down to is you have no idea how to determine the switching structure, right? So indirect methods not only are difficult from the standpoint of timescales, they're also difficult from the standpoint of if you have path constraints, because path constraints are real. Real problems actually have path constraints. You wind up with additional complexity that's so difficult to deal with computationally that you're at a complete loss, all right? So that's the first thing I wanted to talk about today, was just give you sort of mild introduction to path constraints. Now, there are ways that people deal with path constraints. In certain situations, you can, if you know something about the switching structure and it only switches a certain number of times, then you can apply certain types of conditions to be able to determine the switch points in the path constraint. But they're very complicated, they're very specific, and they don't work on any broad class of problems. So they're not very useful from a practical standpoint. Theoretically, they may be interesting, but they don't really help you a whole lot. So what we're going to do today is, for the rest of class, this is the only thing I'm going to do today, is I'm going to get started with numerical methods. And the first thing I want to do is I want to shift completely away from this calculus of variations thing. So this is the beautiful thing about optimal control. Where are we today, February 10th? I've spent like the last 5 or 6 weeks talking to you about nothing but calculus of variations, right? That's all we've done. So now what I'm going to do is I'm going to say, from a practical standpoint, calculus of variations becomes completely useless, right? That's not really true. It doesn't become completely useless. But it becomes completely useless from the standpoint of how you develop methods to solve optimal control problems in practice. And then eventually we're going to try to connect these methods back to the calculus of variations. But in order to do this, I have to completely step away from the variational form. So now, imagine we never had the variational form, right? So I spent 5 weeks, we did all this great theory, and we got to the point where we're like, we can't solve any real problems with this, right? So we have to do it a different way. So today, I'm going to start talking about numerical methods for optimal control. Now, I usually start this off with sort of high-level categorizations, so I'm going to do the same thing here. There are 2 broad categories of numerical methods. The first category are what are called indirect methods. Indirect methods are exactly what we just described through the calculus of variations over the last 5 weeks. The first thing you do is you formulate the first-order optimality conditions using variational calculus. And you attempt to solve the boundary value problem from the calculus of variations. Now, as we just saw, that is not a very easy thing to do, right? So the second class of methods, which is the one that has become sort of the way in which people who actually use optimal control in practice do things, are what are called direct methods. Now, direct method is a completely different way of doing this. So the first thing you do is you parameterize state and or the control via an appropriate function approximation. Now, when you do this, what you're doing is you're saying that I'm going to take the state, I'm going to take the and or the control, and I'm no longer going to be trying to solve for this function u of t, but I'm going to approximate it. So what you do is you say, well, I'm going to say x of t is going to be approximated by some function, and I'm just going to write it like this. C, for I equals 1 to say n of ci times psi I of t. All right? And what that does is it says, well, I'm no longer going to be solving with this elegant calculus of variations thing for this trajectory as a function of time, but I'm going to replace the state with this approximation where these are known functions. These are known functions, and they're often called basis functions or trial functions. I don't really know where the term trial comes from. It's called trial functions. It's not like you're on trial. You're just It's like you try it. That's why they call them trial functions. And then what you do is these things are unknown coefficients or parameters to be determined. Now, you do the same thing with the control. You say the control is going to get approximated by some other set of coefficients. Let's call these coefficients. Let's call these CIX. Let's call these CIU. And I'll call this function alpha of t, alpha I of t. I equals 1 up to n. I have no idea what these functions are at this point. I don't know what these coefficients are. I'm just giving you a general parameterization. And then what we do is you could see that the original optimal control problem, which originally has this Lagrange cost, it's got this Mayer cost, now gets transformed, because it's an infinite dimensional problem, it gets transformed into a finite dimensional problem, right? Because the only things I don't know are these coefficients, CIX and CIU. But I have a finite number of them, right? I've only got n of them, right? So in the parameterization that I've made, I now approximate the integral by some sort of quadrature approximation, and my differential equations are now integrated using whatever I've chosen for those approximations over here. And I'm being very general because I haven't talked to you about what type of direct method that we're going to use yet. So then the second step is that the optimal control problem is transcribed to a finite dimensional optimization problem. And the finite dimensional optimization problem is solved using techniques from nonlinear programming. Now, let's do a specific example of, just like we did with calculus of variations, I'm going to do a simple example or simple formulation of a direct method. So the simplest direct method is called direct shooting. Direct shooting is really simple. It's so simple that it's kind of stupid how simple it is, all right? So the way direct shooting works is this, is that direct shooting is a control parameterization method. It's not a state and control parameterization method. In direct shooting, the only thing we approximate is the control. We do not give a function approximation for the state. So the way it works is as follows, is that the control gets approximated the way I have over there. You say u of t gets approximated as some combination of some coefficients times alpha I of t. Now, what do you choose the coefficients to be? What do you choose those functions to be? The simplest way to do this is to choose these functions to just be simple things like polynomials. So for example, we could choose alpha I to equal the set 1 t squared t cubed up to t to the n. It's really simple. Oh, it's just really simple, okay? Then what happens is, if you look at that, you say, well, now, let's suppose that I don't know what those coefficients C are supposed to be yet, right? But I know the functions, right? So I can plug these functions up here, and if I give you a set of values of C, I know this function, right? Because I know these, and I have to figure out what these are. But if I just gave you a bunch of these numbers, you'd know what this function is, right? So then what you do is you say, well then, given a set of values of CIU, right, from I going from 1 to n, we can do the following. So the first thing we can do is I know that x dot equals f of x and u, right? And I've got some boundary conditions, phi equals 0, where phi is a function of the initial values and the final values. So what you say is, well, okay, what's u? Well, I'm going to call this approximation, I'm going to call it capital U of t, right? So what you do is you substitute capital U of t above, and what do you get? You get x dot is equal to f of x capital U, right? But if I give you a set of values, I can integrate this now, right? Because this is not an unknown function anymore. This is a known function because I gave you those coefficients, I gave you those functions, so you can integrate this. If I give you an initial condition and I say integrate this from t0 to tf, you can integrate it, right? And you'll get some trajectory. It's not going to be the right solution, but you can get some solution to it, right? Second thing you do is whatever method you use to integrate, so I should write this down. So then you integrate these dynamics from t0 to tf using a chosen value of x at t0, right? Because I don't know what this is at this point, right? Phi has to be equal to 0, so I just pick some value and integrate. Phi is probably not going to equal 0, depending upon what I choose. But if you're smart, what you could say is, well, I'm going to pick a value of the initial state that's going to make that thing equal to 0. But the problem is I don't know what the final state is, so it may not actually make it equal to 0. Then the second thing you do is you integrate the cost using the same integration method as was used to integrate the dynamics. So I haven't gone into details on this. I'm going to do it next week. Let's suppose in integrating these dynamics, I chose to use Euler forward or Euler backward or Runge-Kutta or some other method that I know I can pull out of a textbook and use. Whatever method I use to integrate this, I have this cost function now. It's now a function. It's not a cost functional. It's actually a function, right? So I'm going to say J is going to be approximated by this thing. I'm going to call it, let's call it JA, which is an approximation, which is going to equal phi, but it's going to be now plus the integral from t0 to tf of L of x of t, capital U of t, and t, right? Because I'm putting in this function u of t that I know, right? Because if I know this, I can integrate this the same way I integrate this over here, right? Because I know the initial value of this integral is 0, right? So I can do the same thing I told you before, which is I can transform this whole thing to Mayer form by adding a state where that additional derivative of that additional state is equal to L, and I integrate, right? So this whole thing here can be done this way. I could say x n plus 1 dot is equal to L, where x n plus 1 at 0 is equal to 0. So I could almost do it simultaneous with this over here, right? And if I integrate this from t0 to tf, it's like integrating the new system, x dot xn plus 1 dot is equal to f and L, right? I can just integrate this whole thing all at once, right? And I get an approximation for this cost, given a value of u, which I've chosen because I've chosen it to be this kind of an approximation where I have my polynomials something. I just gave you an example here, and I've picked a bunch of coefficients. Clearly, anything I do here isn't going to minimize anything, right? Because I'm just picking. So then what you do is you iterate on this process in such a way that until you satisfy these constraints and you make this as small as possible, right? So look what I have on my hands. Okay, let's look at this at a slightly higher, at a higher level. What are the unknowns? So let's break it down. So what are the unknowns in direct shooting? So what are they? What is it that I don't know here? I don't know those coefficients, right? So my unknowns are these coefficients, CIU, I going from 1 up to n, right? Those are the things I don't know. You could say, well, I don't know this either, but I do. Because in principle, if I give you a function here, I can integrate this. May not be able to integrate it analytically, right? But I can still, on a computer, I can integrate it, right? So I can get a solution. So x is not an unknown. X is actually something that I can determine simply by knowing u. And then, but there's one other, but the thing is, I also don't know the initial condition. So I have to actually figure out what the initial condition is, right? Because I have to keep guessing the initial condition. So the thing is, I don't know x of t0, but x of tf is not a variable in this problem because given a value of x at t0, I automatically can generate a value of x at tf by doing the integration. So these are my unknowns, right? Now, what is the function that's being minimized? There's a function in here. So the function being minimized is JA. It's a function now. It's not a functional, right? Because a functional is a function of a function. This is not a function of a function anymore. It's a function of what? It's a function of those unknown parameters, right? And the initial condition. Those are the only things I don't know in the problem, right? So I have a finite number. So notice this is a finite number of parameters. So I'm trying to minimize this function. I'm trying to find the variables, these parameters that minimize this function. And I've got constraints. The constraints are that phi of x of t0 and t0, x of tf and tf are equal to 0. But you can also add here if you want to. You can say t0 is an unknown, right? So I have to guess that too. So what I'm doing is I'm mapping this whole thing to a finite dimensional problem. So the finite dimensional problem has this particular form. So the abstract form we have the following. Minimize f of z subject to g of z equals 0. That's what I've got. This is z, if you want to call it that. F of z is JA, and my constraints, which are these, is this right here, right? Because this is actually a function of x of t0, and it's a function of x of tf, but x of tf is a function of the result of the integration, which is a function of these parameters, right? So everything here is a function. So this thing actually maps to this function phi, which is a function of x of t0, And now it's a function of these parameters C. It doesn't look like it. But this thing right here is no longer a variable in my problem because it comes from the result of that integration over there, right? So I now have a function where z are these unknown parameters, and I'm going to minimize this function subject to these constraints. What kind of problem is this? This is a nonlinear programming problem. So when you get into direct methods, it's an NLP. Direct methods transcribe your infinite dimensional optimal control problem. This is a very simple direct method. That's why I chose it as a starting point, so you can see what's going on. Because when you get into more complicated direct methods, it becomes very hard to see that this is actually what's going on. But you can see that I started with an infinite dimensional problem. But I chose a parameterization for the control, and I'm going to do what's called direct integration of the dynamics, or explicit integration of the dynamics, and an explicit integration of the cost. I do that, and I do it with a finite dimensional approximation, because the reality is I have no idea whether this functional form that I've chosen is anywhere near correct, right? Let's give you an example. Let's suppose you take the bang-bang optimal control problem, the minimum time double integrator plan. What's the optimal control? It's a constant followed by another constant, right? If I approximate that with a linear function, how good is a linear approximation going to be to two segments that are each constant with a discontinuity in the middle? It's going to be an absolutely terrible approximation. It doesn't make a difference how good I get it, right? So if I plot that, let's just take that for an example, because that's an extreme example, right? So what? Take the double integrator, minimum time double integrator. You know that the solution to the minimum time double integrator has an optimal control that looks like this, where it goes from like min to max, right? Now let's suppose that I approximate that with a straight line. Not a very good approximation, is it, right? Let's suppose I approximate it with a quadratic, or a cubic, or a quartic. Eventually what I'm going to get is I'm going to get something that's going to look like this. If I get a high enough degree polynomial, I'm going to get something that's going to look kind of like that. But no matter what I do, I'm approximating it with a smooth function, but that function's not smooth, right? So no smooth approximation is going to be very good, because I'm trying to approximate something that's discontinuous with something that's continuous and has all derivatives. This thing doesn't have a derivative at the switch point, right? So no matter what I do, this direct shooting method is going to say, well, you told me that you want to use a quadratic approximation. I'm going to find the best quadratic that fits, that minimizes that cost subject to those constraints, and that's what I'm going to give you. I'm going to give you a quadratic approximation, but you know full well it's not a good approximation. So you've just changed the problem to say, rather than find me the optimal control, you're going to find the control that is the best fit for the functional form that you gave me that minimizes your costs subject to your constraints. And it's, in general, probably going to be very suboptimal. It's going to be optimal for the parameterization that you chose, but not optimal when it comes to the actual solution to the optimal control problem. So this creates a big conundrum, because this is a nice way to do things in the sense that now I got nice functions here. I can do whatever I want as choosing functions. I can make this problem into this nonlinear programming problem. There are a plethora of software programs, including the MATLAB toolbox, that will solve a problem like this for you, right? But the question is, when you're all done, what in the world does it have to do with the original optimal control problem? It may have nothing to do with the original optimal control problem. In fact, you may not be able to rationalize, even in the most irrational way, that it has anything to do with the solution of your original problem. You want the solution to the optimal control problem, right? And you're trying to do it by doing some sort of a computational method that does an approximation. Question is, how good is your approximation? Is it close? Is it far away? Now, let's suppose I change the parameterization in this and said, I'm not going to do this anymore, but I'm going to do exactly what we know the solution to this thing is. is it's a constant and a constant. So I'm going to say I'm going to choose the control approximation to be two constants, and I'm going to choose this. I'm going to choose an additional parameter to be the switch time. Now I'm going to get a great solution, right? Because I chose it to be what I know the structure of that solution is, and so if I do it right, I should get the exact solution, right? But you say, well, that's a completely different control, right? Because I'm choosing in one segment, I'm choosing it to be one constant parameter. In another segment, I'm choosing it to be another constant parameter. And there's this unknown switch time. I'm going to add that as a parameter in the problem too. So now I have three parameters. I've got this really simple functional approximation. But the only reason I knew to do that is because I know what the solution looks like, right? If I had no idea what the solution looked like, I would have no reason to choose that as my approximation. So this creates an enormous conundrum because you've just gone from this elegant theory which has all this wonderful geometry and Lagrange multipliers and calculus of variations and flowery math and everything, it's like it's really great, to this other paradigm which is like I want to solve a real problem, right? I'm sitting here at Lockheed Martin and my boss told me I have 2 weeks to be able to solve this problem. That's what I want to do, right? And my boss doesn't care whether I derive 400 pages of variational conditions and say, look, in the last 2 weeks what I did was I got every single theoretical book on optimal control and I did all this fancy math and I've got a notebook full of this stuff. And he said, did you solve my problem? He said, no, I didn't. Well, then what have you been doing for the last week? Well, I've been deriving all these conditions. Turns out that I got all these switch times and I got all this other stuff going on and things, there might be a singular arc here, and he's like, that's great if you're writing a doctoral thesis, but it ain't too good if you're trying to solve my problem, because I got this mission I've got to finish that's got to be done in the next 6 months, and I need a solution to this problem in order to do a preliminary analysis, right? So you're screwed, right? And your boss is going to say, if you're not going to be able to do this, I'm going to go find somebody who does. So then what do? You throw it all away, and you say, all right, let me find the simplest way I can to do this, because that's what's going to wind up happening. And then he's going to come back and he's going to say, how good is your solution? Is it close to the optimal solution? Is it close to burning the minimum amount of fuel? Or are we going to waste a tremendous amount of fuel in the process of doing this because we used your approximation? And you say, I have no idea, right? Because the truth of the matter is you have no idea, right? Because you just did what he asked you to do. He wanted an answer, you gave him an answer. But that's not really what he wants. He wants an answer that's close to what it is that the actual solution would be, so he can go to his boss, who's like 7 levels up from him, who doesn't give a damn about any of this stuff. All he cares about is saving dollars, right? And he wants to know whether or not you're going to burn 3,000 kilograms of fuel or are you going to burn 2,500 kilograms of fuel? Because if you burn 2,500, that saves me 500 kilograms of fuel, and that costs X number of dollars because propellant on a rocket is really, really expensive, right? And I don't want to spend that money if I don't have to, right? So the point is that you have to have an idea as to whether or not what you're doing is actually close to the optimal solution. So this creates an enormous challenge in optimal control, which is where most of the work and most of the research in optimal control is done. The research in optimal control is not in the theory. The theory is well established. The research is done in developing computational methods that you can stake your life on it, that if you solve this problem with this method, you will get very, very close to the optimal solution, and I can quantify for you how close you're going to get to the optimal solution. Because if you're not close, you're not optimal, and if you're not optimal, it may actually cost somebody a lot of money, and nobody wants. And where this actually shows up the most, the two places where this shows up the most are in chemical engineering and in aerospace engineering. Chemical engineering process control is an extremely expensive process. Think about factories that produce chemicals. Dow Chemical. They are, or the petroleum industry. They're doing oil refinery, right? They care a lot about how much their processes cost in terms of energy, because it costs them a ton of money because they're running indefinite processes, right? Once the factory's up and running, it's running for all day long, every day, right? It's doing refinery, or they're mixing chemicals. They're making 409 spray cleaner. They're making it all day long, right? If they have to use more chemicals than they need in order to make that 409 spray cleaner in the period of a year, they will have wasted a tremendous amount in chemicals, and it would have cost them a tremendous amount of money. So even a tiny improvement in their process saves them a tremendous amount of money, and it's also good for the environment. There's all kinds of other issues that come up with this. So these things become really, really important. In the aerospace industry, bottom line usually is fuel, right? Spacecraft propellant costs a lot of money. Rocket propellant costs a lot of money. You're dealing with things like hydrazine. These are very expensive chemicals that if you have to put more on board than you need to, you're going to make the mission cost a tremendous amount. More importantly, normally if you want to put a spacecraft in orbit, you're trying to put payload into orbit, right? So you want to get as much on the spacecraft as you can. Instrumentation, you want to do a scientific experiment. You need to get all these things on. Imagine the space shuttle, which we don't fly anymore. But anyway, the space shuttle, right? It's got humans on board. Think of all the things that you need to put on the space shuttle. You need to put a life support system. You got to have a thermal protection system. You got to have, the life support system's got to have oxygen. You got to have food on board. I mean, there's all kinds of things, practical things that you're like, I need all these things to go to orbit with me because I have people on board, right? And as a result, I need to use as little fuel as possible because I don't want my mass on takeoff to be all fuel. I need it to actually be able to carry these people up to the International Space Station. So this stuff really matters, right? So in the process of doing this, though, you cannot rely on the calculus of variations because these problems get too difficult. So you got to rely on numerical methods. I just showed you a very simple example today of a method that abstractly looks kind of cool. But the question is, does it actually play out well in practice? So we're going to actually spend the next several weeks, and we're going to talk about different numerical methods for solving optimal control problems. And I'm going to have to introduce you to some of the concepts in nonlinear optimization because, as you can see, these problems lead to these nonlinear programming problems. Yes?
Do we know that which method we need to use before solving the problem?
I didn't understand the question.
How do we know that which direct method we have to use to solve a problem?
That is a great question, and the answer is you don't. There are certain methods that are significantly more powerful than other methods. So what I'm going to do is I'm going to do this as an evolutionary thing. I'm going to start with simple things. I'm going to move to more complicated things. And as I move more complicated, the formulations become more general, meaning that those methods can basically subsume the methods that come before them. But I'm going to start with simpler ones. It turns out that, like for example, for launch vehicle trajectory optimization, direct shooting is a great way to go. The reason is because the optimal controls are either linear or quadratic in time, piecewise linear or piecewise quadratic. You can get really close to the optimal solution simply by picking naive approximations like that for like for the pitch or yaw control of a launch vehicle. But if you're solving a more complicated problem, such as like a chemical reactor problem, or if you're solving something that has nothing to do with just a simple, like even like an atmospheric entry problem or an aircraft climb problem, if you're doing like a subsonic or a supersonic aircraft climb, of a commercial aircraft or a military aircraft, turns out that those problems don't have simple solutions. If you use direct shooting, you would get a highly suboptimal solution to the point where you would get something that isn't anywhere close, and it would be a terrible solution. But different methodologies allow you to be able to capture those inaccuracies so that you can actually get quite accurate solutions. But I'm going to start simple, like with this direct shooting, and we're going to work our way forward into collocation, and I'll talk to you about how you actually do those other methods. And then you'll see, and then I'm going to bring some, at some point I'm going to bring some slides in on a computer, and I'm going to show you how some of these things actually play out on some examples, because I can't do that on the board, okay? Because you're going to have to wait. So this is actually, by the way, where this class becomes fun. It really does. I mean, this is the part where you actually can start thinking about using this stuff for things. It's really cool. All right.